Welcome back. Today we're going to be talking about different kinds of bonds. But before we start, make sure that you've already watched the subatomic particles video where you learned about the particles that make up the atoms. This will help you understand why certain atoms make certain types of bonds. Recall that atoms make bonds and form molecules simply to fulfill their octet rule. Okay, so the first kind of bond that we're going to talk about is the kind of bond that carbon makes. And those are called covalent bonds. And you can kind of imagine that you're at a cocktail party and you're holding the chips and somebody else over there is holding a bowl of dip. Now, I could just sit here and eat chips by myself. Or that guy over there can just sit there and eat the dip out of the bowl. But wouldn't we be better if we shared them? If I went over and used some of his dip on my chips, and if he came over here and used a little bit of my chips so he doesn't have to scoop up the dip into his mouth with his fingers. So sharing makes everyone happy. Carbon needs 4 more electrons to satisfy the octet rule, so it's going to share those electrons with some other atoms. And in this case, we're going to be sharing with hydrogen. So what's going to happen is carbon is going to allow hydrogen to use one of its electrons. And hydrogen is going to allow carbon to use one of its electrons. And what's going to happen is they're going to share these electrons. Now, a covalent bond is where you share electrons. And it is a very strong bond because once you get a taste of the chip and the dip together, you don't want to go back to just eating chips. You want chips and dip. So what this ends up looking like is hydrogen, which is atomic number 1, is going to be essentially able to count both of these electrons as its outer shell, which means hydrogen's going to be happy because it's filled that valence shell. It's going to have 2 electrons, so it can count this as 1, 2. But carbon still isn't going to be happy because even though it is going to have 1, 2, 3, 4, and then 5 that it can technically count once it's sharing, that's still not enough. We need to make a couple more bonds. And so what carbon ends up doing is it ends up sharing with a number of different atoms. And what you can see here is that carbon originally had 4 electrons in its valence shell, and those are shown in blue. And carbon is then sharing hydrogen's electron. So each of the hydrogens is happy because it has 2 electrons it can count, and the carbon is happy because it can count not only its original 4 electrons, but the ones that hydrogen is donating to. And so these are very strong bonds, and these electrons are shared pretty equally. So this is what a covalent bond is, a sharing of electrons. Now, let's draw another element. This time it's oxygen, atomic number 8. Go ahead and pause the video, draw out oxygen, and then come on back. Okay, welcome back. Hopefully you got the same thing that I did. So remember, atomic number tells you the number of protons. From that, in a neutral atom, you know the number of electrons, and then all you have to do is fill up those shells from the inside to the outside. Is it fulfilling the octet rule? No, it's not, because it can have up to 8 in this shell, and it needs 8 to be happy, and it only has 6. So it's not happy. So it's also going to attempt to share with hydrogen. So we're going to make a covalent bond with hydrogen. And so this electron is going to be shared between oxygen and hydrogen. And this electron is going to be shared between hydrogen and oxygen, and so on. Oxygen will be able to count 8 electrons, and each of these hydrogen molecules will be able to count 2. What's interesting is, let's go back to our party analogy. Imagine I'm standing there and I'm sharing my chips with the guy that has the dip, and he's sharing the dip with me. But what if I'm really hungry? I haven't eaten all day. I'm starving. What do? You start pulling the chips and the dip towards you. So now I'm essentially holding the chips and the dip, and he can have some, but he's not really getting as much as I am. So that's when you're sharing, but you're not sharing equally. So this is what's called a polar covalent bond. So it's still a covalent bond. We're sharing the chips and the dip, but we're sharing them unequally. So why aren't they sharing equally? This has to do with the properties of oxygen and hydrogen. Oxygen is much more electronegative than hydrogen is, which basically means that it pulls on the electrons. It attracts them much more than hydrogen does. Oxygen is hogging those electrons. And so because the electrons can, when they're shared, not only orbit the original atom that they were around, they are being shared with the new atom. So say this electron right here, I'm going to color it in blue. It can orbit hydrogen, but then it can also orbit oxygen. And in a case of hydrogen and oxygen, it's not going to equally orbit hydrogen and then oxygen. It's going to go around oxygen a bunch of times for every time that it orbits hydrogen. And so you end up with this sort of unequal sharing, meaning for every chip that my friend eats, I'm eating 7 or 8 or whatever it is. And so you have these two types of covalent bonds. You have equal sharing, where everybody's sharing equally. And every time this electron goes around hydrogen, it's also going to then go around carbon. And then you have unequal sharing, and that's called a polar bond. And that's where the electrons are more often around oxygen than they are around hydrogen. So nonpolar is equal sharing. Everybody gets the same amount of chips and dip. Unequal sharing is when, you're just really that much hungrier than the other guy, and you're just sort of taking all of the chips and dip. So what this does is it means that electrons spend more time on the oxygen side of the molecule and less time on the hydrogen side of the molecule, which creates this unequal charge. So this side of the molecule becomes a little bit negatively charged because that's where the electrons are. And remember, electrons are negatively charged. And this side of the molecule becomes a little bit positively charged. So you don't have a charged molecule here, but just because the electrons are having an electron party over here means that this side is going to be a little negative and this side is going to be a little positive. Now, the only elements that can do this, that can sort of unequally share electrons, are going to be nitrogen, oxygen, and fluorine. We don't see fluorine in the human body much, but you certainly are going to see nitrogen and oxygen in the body quite a bit. So what does this mean? When you have something like H2O, which is water, you can actually cause bonds between molecules of water to form because of the attraction of positive and negative things. Remember, positive things like negative things like positive things in chemistry. Opposites attract. So when you have water, the positive end of water is going to attract the negative end of another water molecule. And that forms something called a hydrogen bond. So we have covalent bonds within the water molecule. So this is one water molecule. This is another water molecule. And this is a third water molecule. And within those water molecules, you have covalent bonds, polar covalent bonds holding them together. But the fact that those covalent bonds are polar means that one side of the molecule is a little bit negative and the other side of the molecule is a little bit positive. And so we have this hydrogen bond. And a hydrogen bond isn't really a bond. It's just a very sort of transient, temporary attraction between one molecule and another molecule. And this is what gives water its cohesion. And we use it in lots of places in the body. For example, in your DNA, as well as in protein folding. So returning to our analogy, a non-polar covalent bond is where we're sharing the chips and the dip equally. A polar covalent bond is you're still sharing chips and dip, but they're shared unequally. One person is sort of pulling the chips and the dips closer to themselves, which means one person is kind of getting a little bit less food. And what can happen when you have a polar covalent bond is that you could form a hydrogen bond between that molecule and another molecule. And it's kind of like when you have two people in a situation where you're not getting a lot of chips and dip from your partner, you start looking around to see if maybe there's somebody else around that might give you some of their dip. We're going to draw some other elements now that are going to use a different type of bond. So lithium is atomic number 3, and as we know, that means it has 3 protons and 3 electrons. And so if we were to draw this out, it's going to look like something like that. So you have your 3 protons in the nucleus, you have 2 electrons in the first shell, and then 1 electron in the second shell. Now this definitely does not fulfill the octet rule, because it only has 1 electron in its valence shell. So it can either make a whole bunch of bonds and try and fill up that shell. It has another option. It can lose one of its electrons. So if we do that, if we allow lithium to lose an electron, it becomes what's known as a charged particle, an ion. So in this case, lithium has lost an electron, and now it has 3 protons, but only 2 electrons. So it has more positively charged particles, so it's going to be lithium ion. Now this means that it's pretty reactive. It's very willing to give away that electron. Another element that is pretty reactive is chloride. Chloride is atomic number 17. If you were to draw this one out, you would actually have to go to the third shell because it has so many electrons, right? So it's got 17 protons. It's got 17 electrons, so we first put 2 in the inner shell. We then put 8 in the second shell, and then we fill up as many as we can in the third shell. Now we didn't get to number 8 in our third shell, and remember, the third shell, second and third shell, both want 8 electrons to fulfill the octet rule. So this does not fulfill the octet rule. So what is it going to want to do? So it wants to gain an electron to fill in that missing electron right there. So what we end up doing is we add an electron, and it becomes a charged particle. Because again, we had 17 protons, but now we have 18 electrons. So now chloride has become chloride ion, a charged particle, and it's negatively charged because it has more electrons than it does protons. Now, if you end up letting lithium and chloride be close to one another, what happens? Lithium gets rid of its electron and chloride can pick it up. This results in both of them having their octet rule satisfied. Lithium has a full first shell and chloride has a full third shell. And we're going to make a compound called lithium chloride. And these guys become a molecule because they're attracted to one another. Lithium is positively charged, chloride is negatively charged, and as we know, opposites attract. Lithium and chloride become attracted to one another because of their opposite charges. So this is called an ionic bond, and it's called ionic bond because it's made up of ions. So as long as you remember that an ion is a charged particle, you'll be fine with ionic bonds. Going back to our original analogy of the cocktail party, we have our non-polar covalent where people are sharing the chips and the dips equally. You have the polar covalent where one person is hogging all the chips and the dip and sharing a little bit, but really I'm eating a lot more of the chips and dips than anybody else is. This can sometimes result in those hydrogen bonds I was talking about, where the person who's sharing with me isn't really getting enough, and so maybe they're looking around and seeing who else they're attracted to. And we have our third type of bond, which is the ionic bond, which is where a bunch of people take off their clothes, and so they're naked, and they're standing around at a party, and they're attracted to one another. They're not sharing anything. They're not eating any food or sharing the chips and dip. They're just naked. Water works as a solvent. So when you have something that's an ionic bond, sodium is attracted to chloride. Chloride is attracted to sodium. They're standing around naked at the party, kind of attracted to each other. If you all of a sudden have something that has partial positive charges on one side and partial negative charges on the other side, then those partial charges are going to cause a disruption of the attraction between sodium and chloride. So at the party, if all sodium sees is chlorides, they'll be attracted to one another. But all of a sudden, if sodium's at a party and sees something else negative that she can be attracted to, she's also going to have some attraction to that other negative thing. Likewise, chloride, if the only positive atom around, only positive ion around is sodium, chloride will stand next to sodium. But at a party, if there are other options, chloride will also be attracted to those other options. And so things like salt, sodium chloride, potassium chloride, lots of different ionic compounds that form salts, will dissolve in water because the partial charges on water disrupt this attraction, this ionic bond between the positive and the negatively charged ion. So in the body, water is a solvent because it's polar. The material that's dissolved inside of it is called the solute. And you'll hear me talking a lot about solvents and solutes later, especially in the transport chapter. And usually I talk about water and the stuff. And the stuff is basically the solute, the material that is dissolved inside of the solvent. That's it for today. See you in class.